Okay, class, we finished talking about the mechanisms of breathing in and out. And like I said, I'll have some videos. They'll be included in D2L for you to glance at. This more movie in nature. All right, my next subject I come to is what I call the I to E ratio. I don't think this is in the text, so anyway, I don't believe it is. But the I to E is the inspiration to exhalation ratio, inhalation to exhalation. Okay, let's go through it. If a person has a breath rate, remember normal breath rate is 12 to 20 breaths per minute. Okay, resting. If a person has a breath rate of 12 breaths per minute, then each breath, both inspiration and expiration, is 5 seconds, because 5 times 12 is 60 in a minute. If the breath rate is faster that time, each breath obviously is going to be less than the 5 seconds. That's inhalation, exhalation. If the inspiration time is generally 2 seconds and expiration is 3 seconds, then the I to E ratio is a 2 to 3, and that's kind of what it generally is. No matter, it's kind of a 2 to 3 ratio, even if you have a faster breath rate. Now, the expiration time, which as we saying is 3, is generally no longer inspiration, but that also includes that moment. See, when you breathe in and breathe out, there's a moment when you breathe in that you don't do nothing. And then finally you breathe out. So this is what we call in respiratory the I to E ratio, the ratio of inhalation to exhalation. I wanted to bring that up. All right, let's go a little further. What do I have next? Okay, don't worry, coughing, sneezing, crying, we're not going to worry about that. All right, I'm going now to alveolar ventilation. All right. Now, when you breathe the 500 cc's in, some of it does not go into the exchange zone. Okay, so let me explain it to you. Remember, from the nose and mouth all the way down to the end of the terminal bronchiole was the conduit region. And then after that, starting with the respiratory bronchiole down to the alveolus. So when you bring your air in, some of the air never reaches. There's a column of air all the way down. Some of it is still going to be in the conducting zone. Some of it is of that 500 never got into the respiratory zone. That's what we call dead space. Dead space basically is when the air is there, but it can't mix with the blood. The air is there, but when it can't mix with the blood. Let's see if I put a definition for that. Okay, let's see if I put a definition. So the dead space, there's a dead space, and what the dead space is, the airway pipes prior to the respiratory have walls that are too thick to perform exchange of gases between them and the blood. Thus, these pipes are conduits transferring to that area. Okay, so what that means is that when they're dead space basically is when you got the air there, but it can't get to the blood. You got the air there, but it can't get to the blood. Okay? Now, I come back here. That means based upon the design of the lung, that's just there. That's what we call the anatomic dead space. The anatomic dead space. That's just there. Okay? The anatomic dead space. Now come over here. I want you to keep that in mind. That of that 500 cc, some of it, and the amount using that number is about 150 cc's. So about 500, you breathed in 500. About 150 cc's is in the nasopharynx, oropharynx, all those tubes before you get to the respiratory zone. That would be your God-given anatomic dead space. So if we look at the alveolar ventilation rate, now I'm going to come here, the alveolar ventilation rate. The alveolar ventilation rate is basically how many milliliters a minute do you bring in, okay, how many milliliters a minute do you bring in? That's the alveolar ventilation rate, okay? Now, when you look at that, that means what's your frequency of breathing? If it was 12 and you brought 500 in, you would be bringing 6 liters in. But since part of that 500 was in the dead space, I have to subtract that out. Since part of that's in the dead space, I have to subtract that out. Okay? So what really got to the alveoli was not all 500 cc's. It was around 350 cc's if we took the 150 out, which was in the conduit zone, shall we say. Okay, so we're going to come back here again. Okay, so we have what we call ventilation to perfusion coupling. Now, this is kind of gets deep here now. Ventilation to, because what's the job of the airway? The job of the airway is for the alveoli to meet the blood. The alveoli to meet the blood. So think of 2 train cars. Now let's think of this. Okay, this is kind of an example, if I can think of something here. Okay, we got 2 railroad tracks close to one another. Okay, one train is going one direction and the other train is going the opposite direction. Let's say there was somebody that was trying to throw something from one train to the other. So as each boxcar came, so one boxcar would try to throw to another boxcar. Then that boxcar would move and another boxcar would come on the other side. So you're trying to do a one-to-one. You're trying to do a one-to-one. So you say, what do I mean by ventilation perfusion? Okay. The ventilation would be this here, the minute ventilation. The perfusion would be the blood flow. Now remember, the average cardiac output is 5 liters a minute. So that means about 5 liters a minute is going, go back and think of your cardio. About 5 liters per minute is going to the lung. Okay? On the ventilation end, though, we said if you had 12 and 500, that would be 6 liters. So you'd have 5 liters of blood, but 6 liters of air. But you really wouldn't have 6 liters of air going to the good spot, which would be the alveoli, because I need to subtract out the 150. So then the ventilation to perfusion would be more equal, because now I would have ventilation, and what's that, 12 times, let's look, let me calculate that, give you that. So I'm looking at 12 times 350 equals, that's 4,200. So I would have about a 4,200 ventilation actually going to the exchange divided by 5 liters, which would be the blood flow. That would be kind of my ventilation to perfusion rate. Okay, my ventilation to perfusion. So the total ventilation is the amount of air coming into the lungs in a minute on average. That's the total ventilation. But the exchange ventilation is how much air is going to the exchange zone. This is the amount of air in the lungs doing it minus the dead space. Q is the perfusion. So in other words, in respiratory, we call it the V to Q ratio. The V would be the ventilation and the Q would be the perfusion. The V would be the ventilation and the Q would be the perfusion. And the perfusion is the blood flow going to the lung, which is 5 liters. So that's what we call a V to Q ratio. Now, when we look at the lungs, we actually zone the lungs out. I'll use this. In the upper part of the lungs, you have better air. You remember air rises. So in the upper part of the lungs, you have quite a bit more ventilation than you do perfusion, because you'd have to push the blood up against gravity. So we zone it into zone 1, 2, and 3. That zone 2 region is about an equal V to Q, and the zone 3 down here, it would be better perfusion because blood could fall down from the heart. See, the heart's about up in that area. So that's kind of what you're looking at there. So that's what we call the V to Q, because what your job is to put air into the blood, And that's what we call the ventilation to perfusion. Now, come back to that dead space issue. Now, I want to come back to that dead space issue. Let's go here. All right, we had the anatomic dead space, which is the God-given dead space. But I want to bring up another one called physiologic dead space. Let's see where I put that. I got it right there. The physiologic dead space equals to the anatomic dead space plus alveolar dead space. Now let me say this. This is really what you have in your body. Let's just be honest. This is what you really have is physiologic dead space. It equals to your anatomic dead space, which is just there. That's in your anatomy. Plus bad airways. Hey, we all do. Some of our airways have collapsed through the years. So the physiologic dead space is really the anatomic dead space plus bad airways that should have been able to work, but they don't. Okay? Out of the bloodstream. But for some reason they cannot. If an individual has none of these bad airways, then the physiological equal to anatomic, but that's not true. Okay? All right. So that's what we call physiologic dead space, which is the anatomic plus the alveolar. So what have we discovered? We talked about alveolar ventilation. Let's go back and study it. Ventilation to perfusion coupling, which is the V to Q ratio, which is what? The V to Q ratio. Okay. We talked about that. We already talked about surface area. Remember this, we have about 300 mil alveoli. They're very thin. This is the surface area. A little discussion there. Here again is respiratory dead space. Okay. Physiologic dead space. Don't worry about that. That's perfusion. The Q is the blood perfusion rate to the lungs in a minute, which is really the cardiac output, approximately 5 liters per minute. Though the blood supply to the lung as a whole is equal to cardiac, different regions of the lung get varying blood supplies. Most consider there are 3 zones. The upper zone, which is above the heart, gets the least blood but the best ventilation. Air rises. The middle zone, which is the level at the heart, gets an equal, kind of an equal V to Q. And the lower, because of how blood can drop, is heavy, then it has a better, then there's more perfusion than ventilation. Okay? Now, if the blood can get to an area of diffusion, but the ventilation can't, it's called a shunt. So the shunt is opposite of dead space. Let me bring that up to you. Let's see where we go with this. All right. If blood can get there, but air can't because it's too thick. If blood is there, but air can't get there because it's too thick, that's what you call dead space. The air is there, but it can't get to the blood. But if you have a situation, okay, if the blood can get to the area, but the ventilation cannot, that's a shunt. So the blood is just passing through. What the body does is close off shunts. Okay? So let's think about it. Okay, how can we put this? You had atelectasis. Okay, the guy was a football player. He got hit in the chest. Some of his residual volume came out. The alveoli collapsed. Okay, blood is still going in that region. Blood is still going to those alveoli. So it's being shunted across because there's no air going there. There's no air. Remember what I told you happens is diametrically opposite to what normally happens. That a shunt in the lung gets closed off. You would close that blood supply and redistribute it to better areas. So shunts physiologically get closed off. They get closed off. Let's see if there's anything else. We already talked about flow before. Airway resistance, I'm not going to get into that. You can look at that yourself. We already talked about resistance formulas. So really, I am going to say that this closes out. We already talked about compliance, so I'm going to close this one out. Okay.